How to explain this? According to series, hydrodynamic simulations, in particular the Vela simulations, suggest as galaxies head towards quiescence, they need to build up their central dense regions through the highly distributive gas accretion. And this mechanism is also known as the wet compaction often. So in this scenario, there do have a physical link between the structural transformation and quenching. However, on the other side, the progenitor effect can also contribute to the observed signal. So in the expanding universe, compared to galaxies formed later, galaxies formed earlier are actually naturally expected to be smaller and denser, just as the universe was denser earlier. So studies such as this one from Lilly et al. In fact show, purely by the progenitor effect, they can also reproduce the observed correlation between the star formation properties and the structural properties. So our purpose of the study is attempt purely empirically to answer if there's really a causal link between the structural transformations and quenching. And the key is to measure and then to mitigate the progenitor effects from the observed signal. And this requires us to empirically separate galaxies formed at different epochs and have different assembly histories. So to do so, we actually utilize this fully Bayesian assay defeating codes prospector. Then we reconstruct the non-parametric star formation history of galaxies. So just to show you some tests we have done to test the robustness of the reconstruction, here I'm using the synthetic observations that were generated for Redshift 2 galaxies from the TNG simulation, where the black curve shows you the true star formation history, and the red curve shows you the recovered one from the prospector. You see the great agreement between the two. So the other test we have done is purely empirical. So we look at the quiescent galaxy from the legacy survey, where each galaxy has the deep VLT spectroscopy available. So here I'm plotting the stellar age sensitive spectral features, H delta A versus the D4000 break. And each galaxy is color-coded according to the prospector-derived mass-weighted age. You also find a good agreement. So these two tests suggest that the non-parametric star formation history from prospector are statistically robust given the data quality we currently have. So then we go to the real galaxy, we run prospector, do the non-parametric star formation history for a sample of galaxies at redshift between 1 and 4, and have stellar mass larger than 10.3, selected from the CANDLE's Cosmos and Goods field, where in each field we have almost 40 bands photometry collected in this field. And here it's just showing you one example of the data coverage we have in the sample galaxies. And so before I'm moving forward, I also want to mention this parameter Z form that I'm going to use in my discussion. So we call it the formation redshift, which is defined as a redshift when the time interval between the Z form and the time of observation is equals to the mass-weighted age. So it will be used as a proxy for the formation time of galaxies. So first thing I'm showing you is the relationship between the RE versus Z form and sigma 1 versus Z form for quiescent galaxies and for star-forming galaxies. One thing you notice is that the structural properties of galaxies depends on Z form. Galaxies with larger Z form, meaning they actually formed earlier, tends to have smaller sizes and larger sigma 1. And this is a progenitor effect. And you can see here, if we just mix every galaxy together, even within our sample, up to 50% change in RE and up to almost 1 dex change in sigma 1 can be fully accounted for solely because of the progenitor effect. Therefore, the progenitor effect has to be taken into account before we interpreting the observed structure evolution. So next, instead of bundling all galaxies together, we first bin galaxies according to their Z form. Then we review the plot of the delta main sequence versus sigma 1. You should note, because now within each panel, galaxies have similar Z form, the progenitor bias effect should pretty much already be mitigated. But yet, you still find this pistol-shaped pattern, telling us the progenitor effect alone is actually insufficient to explain the observed correlation. This is actually a strong empirical evidence we either need a causal link between the structural transformation and quenching, or there's a yet unidentified process that drives the both. So we continue to study the relationship between the morphology of galaxies and their whole assembly history. So I bin galaxies into 4 groups: extended and compact quiescent galaxies, and extended and compact star-forming galaxies. Let's first look at the average star formation history of individual groups. Again, each panel only shows you galaxies have a similar Z form. You see the dramatic different assembly history for the extended and compact quiescent galaxies. For compact quiescent galaxies, they are more like a typical quiescent galaxy, which have an early starburst, followed by a gradual decline of the star formation rate. While for the extended quiescent galaxies, they are more like the post-starburst. Namely, they have just experienced a recent starburst within 100 megayears ago. So unlike these significant differences we see here, if you look at a star-forming galaxy, on average, it seems the differences are pretty subtle. So we continue to look at the individual star-forming galaxies. And in particular, we visually inspect individual star formation histories and identify the star-forming galaxies show such multiple star formation episodes. As you might notice, because star-forming galaxies certainly have an ongoing star formation. So those with multiple star formation episodes can be considered as a star-forming galaxy, have the clear presence of the older stellar populations. So then we plot the fraction of such star-forming galaxies as a sigma 1. What you find here is that compact star-forming galaxies are much more likely have experienced multiple star formation episodes. And interestingly, if we also plot the fractional of star-forming galaxies have a surface index between 1.5 and 3, or in other words, their light profile suggests their structure is a dense central core plus a diffuse outskirt, you find this very similar increasing trend. And we think the whole thing is consistent with the notion that high redshift star-forming galaxies assemble their central region earlier. A more direct and informative test we want to do to constrain the evolutionary mechanism of galaxies is to reconstruct the structural evolution of individual galaxies. But it is really non-trivial. Why? Because in observations, the structure of galaxies is only known at the time of the observations. However, with the star formation history, we propose this novel but still purely empirical approach to infer the structural property of galaxies back in time. And the only key assumption we make is that the structure of a galaxy is known once its redshift, stellar mass, and star formation rate is known. So what we do for each galaxy, we first use its star formation history to predict how the star formation rate and stellar mass looks like back at the time they form. Then we go to the real galaxies which are actually observed as they form, have similar star formation rate and stellar mass. And then we use the average structural properties found in step 2 as the inferred structural properties of galaxies as they form. So here I'm showing you the reconstruct evolution of sigma 1 and sigma e for individual galaxies. Here I group galaxies into 4 groups according to their delta main sequence. And here the large arrows shows the median evolutionary vector for each individual groups. And each arrow starts from the property that we inferred as they form and ends at the property that I actually measured as they observed. So, and in the bottom right corner, I also plot the approximate prediction from the simulation of the Vela simulation. So as you can see, our reconstructed evolutionary vector of quiescent galaxy is actually in quantitative agreement with the simulations of the wet compaction. And you can also compare the inferred trend between different structural properties. Here on the y-axis, I'm plotting the inferred evolution of sigma 1 minus the inferred evolution of sigma e. As you can see, when galaxies are still in the star-forming phase, the inferred evolution of sigma 1 is larger than that of sigma e, suggests when galaxies are preferentially grow in its center when it's actually in the star-forming phase. While in opposite, when star formation quenches, we find the evolution of sigma 1 slows down and even becomes slower than sigma e. So everything I showed above is about inner regions of galaxies, right? Within one KPC or within RE. So how about outskirts? So here I'm showing you the distribution of the excess shrinkage factor, which we defined as the inferred size change from our reconstruction divided by the expected size change due to the adiabatic contraction. So as you can see, for quiescent galaxies, the inferred change of RE is about the same as you expected from the adiabatic process. However, if we use the protrusion radius as a characteristic size of galaxies, you find it's actually much smaller than what you would expected from the adiabatic contraction. However, I should emphasize here, we are not suggesting the size change is due to adiabatic process. What really is showing here is suggest the mass growth really happens at center, while the outskirts seems to be less affected. And finally, beyond the morphology, we eventually want to expand the study to the dynamical evolution, because that's not only important for the galaxy evolution, but eventually also important for understanding the interplay between baryonic and dark matter particles. However, we don't really have enough dynamical information for cosmic new galaxies, so we go to the lower redshift for the quiescent galaxies in the legacy. And because for legacy galaxies, most of them only have the unresolved stellar kinematics from the integrated spectrum. So we study the relationship between the velocity dispersion from the stars as a function of the axis ratio. A decreasing trend of sigma with axis ratio would be an empirical evidence that systems do have a significant rotation. So here I'm being galaxies according to their mass-weighted age derived from perspector. I also beam galaxies into two stellar mass beams. So the first takeaway from this plot is that for the young, massive quiescent galaxies, regardless of their mass, we see a decreasing trend between sigma and the axis ratio, suggesting these massive systems do have significant rotation right after quenching. However, as you can see, for the very massive galaxies, the decreasing trend seems to become less prominent, while for the lower mass one, this decreasing trend seems to persist. So to better show this mass dependence, we run the correlation test. We first rank the sample according to their stellar mass weighted age. Then we run the correlation test, start from the 30% of sample, then we keep adding older and older quiescent galaxies into the correlation test and see the change of the correlation coefficient. So here, as you can see, for very massive galaxies, as we adding older and older quiescent galaxies to the test, the negative correlation flattens. While for the lower mass guys, it seems this remain unchanged. This tells us we actually see the after quenching dynamical transformation, but that's only seen in the very massive galaxies. So to quickly summarize, we find the significant correlation between the star formation history of galaxies and their morphology. We show that the progenitor effects is clearly observed and accounted in our analysis. It alone is insufficient to explain all the apparent correlations. And finally, with this high-fidelity star formation history reconstruction, we propose this novel approach to empirically reconstruct the structural evolution of individual galaxies. And finally, if we put everything together, we converge to this general picture. For star-forming galaxies, as they head towards quenching, their structural change preferentially happens at the center. Right after the quenching, although the galaxy seems to already develop a central dense core, but the outskirts seems to be less affected, and they still have a significant rotation. And a long time after quenching, the structural transformation continues, but it has a stellar mass dependence. But maybe the processes such as a minor merger are more frequently happen in the more massive halos. We find for these very massive galaxies, they eventually become a velocity dispersion dominant system, while for the lower mass ones, they still have some rotation remaining. Then that's pretty much my talk. Thank you, everyone.
Thank you. Have time for maybe one question.
Thank you for that nice talk. I was just interested in your plot. Could you go back one slide? That one, yeah. So did you, I'm just surprised by some of those objects at low sigma 1, but also that are they're quenched as well.
Yeah.
Are those ones? Did you take the satellites out of the sample, or
No, here are really massive. They're all about 10.3.
they're all
so
really massive?
I would say at this redshift, maybe they're less likely to be satellite. But one thing I didn't really get a chance to tell is that, so we actually use Mark's machine learning catalog to cross-match a sample. We do find for those quiescent galaxies seems to have extended morphology. Their star formation history is like a post-starburst, but their morphology also is more likely to be disturbed in the way that they more have the irregular morphology and likely to be identified as mergers based on Mark's machine learning catalog.
No, I'm just saying because you were saying that there was still a correlation, like there's still the L shape, but I don't see, like there's no, the L shape has been destroyed in the last two diagrams. So I was just asking how you
Yeah,
see those.
So I don't know. So I don't have an answer for that. But I think eventually we want to study if this compaction only happens after some redshift because you really need some time. Maybe when the formation redshift becomes so high, some other things could happen. But that's just my speculative answer, not really the answer.
Thank you so much.
Could we go ahead and change the computers there?
So I'm going to take your questions.
Yeah, thank you very much for the nice talk. I had two questions. One is, you separate objects in two classes based on compactness, and you see this difference in star formation history. I was wondering if this is a continuous trend. So how much it depends on where you put the threshold, or if you just color code, for example, by sigma 1, you see this.
So here's my question. So I didn't get a chance, but in the paper we basically say, instead of use a Durkheim main sequence to separate quiescent X star forming, we try to use the UVJ, nothing changed. Instead of using sigma 1, we use sigma E or the other compactness metrics to separate the galaxy into two samples, nothing changed. So basically it seems to me it's not really sensitive to the criteria we use to separate the four subgroups.
Right, but I'm saying if you don't separate, if you just, do a
continuous change, right?
Do you see this a smooth transition, or?
I have not really done that, but that's a good suggestion. We can do that, yeah.
And then, if I may, you didn't mention what quenchers. So, looking at the star formation histories, can you know, or infer what is the quenching mechanism?
Oh. Well,
so is it?
At the moment, we're trying to be purely empirical. So, and when it turns to the specific mechanism drives the quenching, we're still working on that. Yeah.
Thank you.
Okay, can you hear me? This is going to be